First, we're going to look at internal mail flow. And to get things started, I'm just going to go through a few important definitions that you'll need to understand and keep in mind as we go through this internal mail flow module. Then we'll take a look at some internal mail flow scenarios. We'll dive into features such as shadow redundancy and safety net, and then take a look at how receive connectors work. The first definition to understand is routing destinations. Routing destinations are the final destination that Exchange has determined for a message based on the recipient information. Routing destinations can be one of the following. They can be a mailbox database, and obviously that is for internal recipients. A routing destination can be a connector when the recipient has been determined to be outside of the organization. So that will be a connector that provides a route to the external domain or mail system for that external recipient. A distribution group expansion server can also be a routing destination if one has been specified for that group. Otherwise, any mailbox server can perform the distribution group expansion. When a DG is expanded, the message may get duplicated into multiple messages, each with different routing destinations. A good example for this is a distribution group containing internal mailboxes and external contacts. It needs to be broken up into separate messages for those different destinations. The internal mailboxes will have a routing destination that could be a mailbox database, and the external contacts will have a routing destination that is likely to be a send connector for reaching the external domain. Each routing destination has one or more mailbox servers that are responsible for delivering messages to that destination. Those servers are referred to as a delivery group. A delivery group could be a database availability group, or DAG. The DAG members are considered the delivery group for any mailboxes that are hosted within that DAG. A group of mailbox servers in an Active Directory site is also potentially a delivery group. If a mailbox is not hosted in a DAG, then any of the mailbox servers in the same site as the mailbox itself are used as the delivery group. Another potential delivery group is the connector source mailbox servers. If a message needs to be sent over a send connector, then the source servers for that connector are the delivery group. And a delivery group can also be an Active Directory site. If a hub site has been configured and it is the least cost route to the destination, then the mailbox servers in that site are a delivery group. And we'll learn more about hub sites shortly. Here's a simple example of routing. Let's say that a scan to email device on the network sends an email message. It's received by the front-end transport service first. Front-end transport has to make a decision quickly about where to route that connection based on the recipient of the message. If it's a single recipient in the same site, front-end transport will route the connection to the transport service, which will route it to the mailbox transport service, which connects to the database to deliver the message. The routing destination in this case is the database hosting the mailbox, and the delivery group is the mailbox server in the site. If the recipient is in a different site, front-end transport will route the connection to a transport server in that other site. So as you can see, the basic rules apply here. Front-end transport can talk to the transport service on the same or on different mailbox servers, and then transport talks to mailbox transport, and mailbox transport talks to the databases. Well, what about if there is a database availability group involved? The routing destination doesn't change. That's still the database hosting the mailbox, wherever that database is active in the DAG. But the delivery group changes because a DAG is a delivery group, and front-end transport will prefer a DAG member in the local Active Directory site. So in this case, front-end transport would route the connection to one of the DAG members in San Francisco. The transport service on that DAG member can then route the email to the mailbox transport service of the DAG member hosting the active database. where it's delivered to the mailbox. Now that's emails coming in via front-end transport. But similar routing occurs for other internal messages, such as between two mailbox users. Mailbox transport sends the message to transport, and routing decisions are made from there. Now, each of those examples were for single recipient emails. What if there's multiple recipients for an email message? The routing destination for a distribution group isn't known yet. So front-end transport or mailbox transport will just route to the nearest transport service. After the distribution group expansion occurs, routing decisions can be made then. If a message has multiple recipients in the to field, the first 20 of those recipients are used to work out where the best transport service is, and then that transport service decides what to do from there. For an email to get from the sender to the recipient, Exchange needs to work out how to route the message to that recipient. When the message is processed by the transport service, the categorizer will calculate the least cost route to the delivery group for that recipient. Now, what exactly does that mean, least cost route? Let's say, hypothetically, we have an Exchange 2016 organization with servers in 4 different cities. Each of those cities is a separate Active Directory site, all within the same Active Directory forest, all part of the same Exchange organization. For the Active Directory replication topology, there are AD site links configured with a cost value that represents the relative network speed of the WAN connections between the sites. Generally speaking, the lower the cost value for an IP site link, the more speed or bandwidth there is available for Active Directory replication traffic. Basically, this is a way to control which WAN links are used for replication traffic, which optimizes overall replication performance between the sites. Exchange looks at the same IP site cost links when calculating the least cost route between 2 servers in the same organization. The cost of each IP site link along a route is added together to get the total cost of that route. So in this example, for an email to get from Los Angeles to New York, the least cost route is via the Chicago site. But that's just the cost of the route in terms of IP site links. From a network connectivity point of view, the Los Angeles server will still connect directly to the New York server. The physical path that the packets for that network connection go over will be controlled by the routing configuration of the WAN itself. Now, logically, you'd expect the network routing to prefer the most efficient route as well, and a well-designed network has IP site links in Active Directory configured in a way that should align with the underlying network routing behavior. So if the 2 servers connect directly to each other, well, what's the point of working out that Chicago is the least cost route between Los Angeles and New York? There are 2 answers to that question. The first, if there's an outage in New York, Exchange will try to send the message to the nearest site where it can be queued until the New York server is online again. This is referred to as queuing to the point of failure. So in this example, the message will be sent to Chicago and queued there. It won't stay in Los Angeles in a queue on the Los Angeles server. The exception is if the mailbox is hosted in a DAG. If a DAG is the delivery group for the message, then the sending server will try to deliver the message to the closest DAG member, followed by any DAG member, and only if no DAG members are available will it fall back to queuing at the point of failure. The second answer is if a hub site is configured. When an AD site has been configured as a hub site, and that site exists on the least cost routing path between 2 other sites, the message will be sent to an Exchange server in the hub site instead of directly to the destination server. To configure a site as a hub site, you would run the set AD site commandlet, providing the name of the site and setting the hub site enabled property to true. It's possible to have a hub site that is not used for routing messages if it is not on the least cost routing path. In this example scenario, if the IP site link between Los Angeles and New York had a lower cost than the links going via Chicago, then even though Chicago is a hub site, the messages from Los Angeles to New York would not route via that Chicago hub site because it's no longer the least cost route. You can also override the cost of an IP site link by assigning a specific exchange cost to the site link. You do this by running the set 80 site link commandlet and using the exchange cost parameter to set that value. This is useful in situations where the Active Directory topology doesn't precisely match up with how you want your exchange routing to behave. For example, let's say that even though it's fine for Active Directory replication to occur over the Los Angeles to New York link, you still want email to route via the Chicago hub site. So by lowering the exchange cost of the LA to Chicago link, you can ensure that Chicago is used as the least cost route and the hub site is used as intended. Hub sites are actually not all that common these days, thanks to the ready availability of cheap network bandwidth, but it is still a concept that you need to be aware of as you prepare for the certification exam. Next, let's talk about shadow redundancy. The goal of shadow redundancy is to improve the availability and resilience of email in transit. In other words, email that is still traveling through the transport pipeline to its destination. Shadow redundancy first appeared in Exchange 2010, and then it was improved in Exchange 2013, and it's still with us today in Exchange 2016. The basic approach of shadow redundancy is to make a copy of email messages to another mailbox server in the organization in case of a failure of the server that is processing the message. So let's look at an example. An email has been sent from a device to an internal recipient. Front-end transport has proxied the connection to a transport service, and before the transport service acknowledges receipt of the message, a copy of the message is made to another transport service. There's a few variables at play here. If the server is not a DAG member, a mailbox server in the local Active Directory site is used as the shadow server. But if the server is a DAG member, another DAG member is used as the shadow server. If the DAG spans multiple Active Directory sites, shadow redundancy will try to pick a DAG member in a different Active Directory site so that you get site resilience for the message as well. If you've already watched course number 1 in this series, then you might recall that this is one of the benefits of properly defining your Active Directory site boundaries when you deploy a DAG across multiple data centers. If you use a stretched IP subnet across both data centers, or you just forget to configure your site boundaries, then shadow redundancy can't make the best decision about where to place the shadow copy of the message. When the shadow copy has been successfully created, the first mailbox server sends back the acknowledgement to the sending device or server, and the idea here is that the acknowledgement is not sent until the shadow copy is created, so that if there is a problem and the mail item is lost in transit before the final delivery to a mailbox, the original sending server never received acknowledgement, so in theory it will queue and retry the message that it was sending. Now that will depend on the characteristics of the sending device or server. It's possible that some less intelligent devices will simply fail the SMTP connection and they'll never retry. But for most situations, this is how shadow redundancy helps. So now we've got a copy of the message safely stored in a shadow queue on another server, and delivery to the final destination can be completed. Shadow redundancy is enabled by default. This is an organization-wide setting. It's not a per server setting. And The recommendation is you should just leave it enabled. The other configuration to consider is whether to accept or reject messages if the creation of the shadow copy fails. Now consider that shadow copies will always fail to create if you've got a single server environment or a single server site, because a single server or a non-DAG member would have no other server in the same AD site on which it can create the shadow copy. So this setting can only be set to reject messages if you have a DAG. Now, why would you choose to reject messages? Perhaps resilience is more important to you than continued delivery, and you'd prefer that the sending server queue those messages and then retry later. But if you've got a 2-server DAG within one site, and one server is down for a fault or perhaps for planned maintenance, that setting will actually cause all messages to be rejected while that DAG member is down. So use that option with care. For the most part, you'll just want to leave the shadow redundancy configuration alone. And just remember that it is an organization-wide setting and not a per server setting. And it's configured by running the set transport config commandlet. Next, let's talk about shadow redundancy's cousin, which is safety net. While shadow redundancy is responsible for protecting messages in transit, once the messages have been delivered, that's where safety net takes over. Safety net stores copies of successfully delivered messages so they can be resubmitted into the transport pipeline if necessary. Messages are resubmitted after a lossy failover of a database in a DAG. A lossy failover is when a database fails over to a passive copy that has not yet received all of the transaction log updates from the active database copy. In course 1, we looked at how the DAG will accept a small amount of data loss by default during a failover, and safety net is how it makes up for that data loss by resubmitting messages. The other resubmission scenario is when a lagged database copy is activated after removing all of the transaction logs that are in the database copy's replay queue. Usually this is done when trying to avoid database corruption from replicating to the lagged copy, and since the transaction log data is removed and can't be used to bring the database copy up to date, resubmission from safety net occurs instead. The default safety net hold time is 2 days, and that is configured at the organization level. If you have lagged database copies, the hold time should be configured to match or exceed the longest lag time on your lagged database copies. And to configure that safety net hold time, we just use the set transport config commandlet and set the safety net hold time value accordingly. And the example that you see in front of you is a value of 10 days. So here's an example of safety net in action. Let's say a message has been successfully delivered to the recipient. After successful delivery, both the primary copy and the shadow copy of the message are moved to safety net, which is part of the transport database. Before the changes in the database have successfully replicated, a failure occurs on the server that is hosting the active database copy. Now perhaps the underlying storage fails or the entire server fails. Either way, the DAG has to perform a failover to a passive copy of the database. And since replication was not completely up to date, this would be an example of a lossy failover. The database won't necessarily fail over to the DAG member that hosts the other safety net copy. That's not really important for this scenario. The important thing is that safety net has a copy of the message available for resubmission. So where shadow redundancy ends, that's where safety net's job begins. And the two of them work together. Safety net is made redundant by shadow safety net, as long as shadow redundancy hasn't been disabled in your organization. That way, if the primary safety net is unavailable for some reason, say that's the server that happens to have crashed, then the resubmission requests can be serviced from the shadow safety net instead. Email messages are passed between clients, servers, and transport servers using connectors. Receive connectors are used to receive messages. The other type of connector is a send connector, and we'll look at those in the next module. There are 5 receive connectors configured on an Exchange 2016 mailbox server by Exchange setup. So these are configured for you when the server is first installed. 3 of the connectors are bound to the front-end transport service, and 2 of them are bound to the transport service. The default front-end server name connector, and server name here is just a placeholder. By default, these will be named with the actual server name. So default front-end listens on port 25, that's TCP 25, so that's your standard SMTP port. And it's the entry point for email from non-Exchange systems into the organization. The client front-end connector listens on port 587. This connector requires client authentication, and it's typically used for secure authenticated SMTP, so that is protected by transport layer security, and that's typically used by any authenticated clients, and a good example of that is POP and IMAP clients. The outbound proxy front-end connector listens on port 717. This connector is only used if a send connector in your organization is configured to proxy outbound email via the front-end transport service. And by default, send connectors are not configured to do that, so you'll probably find that this particular connector is almost never used in the real world. It's certainly not used by any other servers or by any clients for connecting to Exchange. On the transport service, the default connector listens on port 2525, and this connector accepts connections from other transport services on the same or on different servers. So that can be connections that have been proxied through the default front-end connector, from edge transport servers, from mailbox transport services, or from other transport services on other servers. Finally, the client proxy connector listens on port 465, and this connector accepts client connections that have been proxied by front-end services. You really should not modify the default receive connectors on your Exchange servers. There are only a few cases where modifications to those connectors are okay, and that is if you're changing the message size limits, if you're changing the rate limits, or if you're configuring a TLS certificate to use on a particular connector. Now let's look at a particular type of receive connector, which is generally referred to as a relay connector. In most organizations, there are several devices or applications that need to use an SMTP service to send email messages such as notifications or alerts, or if you've got a scan to email device. An Exchange 2016 server can provide that service for you. However, the configuration required on the server depends on the SMTP relay requirements of your scenario. There are generally 2 types of SMTP relay scenarios that Exchange Server 2016 is used for. You have internal relay, which is devices and applications that need to send email messages only to internal recipients in the Exchange organization. And we have external relay, which is devices and applications that need to send email messages to external recipients. Internal relay works without any special administrative steps or changes required. The default front-end connector is already configured to accept SMTP connections from anywhere, and the Exchange server will allow an anonymous sender to send email to any internal recipients, since that is also how internet email is treated. However, if an anonymous sender tries to send to an external recipient, the relay attempt will fail. There are 2 ways you can resolve this and allow your devices and applications to send to external recipients. The first is to use authentication for those SMTP connections. So you saw in the previous video, there is a connector all pre-configured, ready to go, and specially designed for handling authenticated SMTP connections. And any clients that do authenticate, when they connect to that connector, will actually be able to send to any recipient, whether that's internal or external. The other method is to configure an anonymous SMTP relay connector. An anonymous SMTP relay connector is a receive connector that is also bound to the front-end transport service, so it's listening on port 25, and that is configured to accept unauthenticated or anonymous connections from specific IP addresses or IP ranges, and it will allow those specific IP addresses to relay to external recipients. Now, how does Exchange know which of two connectors, both of which are listening on port 25, should handle the connection? The answer is that the most specific match wins. The default connector has an IP range that is effectively anything. So that is the least specific configuration. If you have a connector with a specific IP or IP range that matches where the incoming SMTP connection is from, that more specific match will mean that the connector handles the SMTP connection. You do need to be careful with this because source IP addresses can be masked by NAT devices like routers and firewalls and load balancers, but other than that, it's quite a simple configuration and it just works. So on to the demo. Globomantics has a monitoring software running on the San Francisco domain controller that needs to send email alerts to an external address. So we're going to have a look at configuring a relay connector. Let's start on the San Francisco domain controller. And we'll just have a look at what happens when we try to connect to the Exchange server using SMTP and try and send email to an external email address. And we can clearly see that an error is received, unable to relay recipient in a non-accepted domain. So gmail.com is not one of the accepted domains for the organization. So over this anonymous SMTP connection, we can't relay email to that domain. So in the Exchange admin center, let's go ahead and create a new receive connector on the San Francisco Exchange server. So we'll stick to the naming convention and just call it relay SF Exchange 01. So that's consistent with the naming convention for the other receive connectors on the server. We need to make sure that the role is set to front-end transport, and we can just leave the type of connector as custom. The network adapter bindings do not need to be modified. It's fine for this receive connector to listen on port 25 on all available IPv4 addresses, and it's here in the remote network settings where we define the specific IP addresses or IP ranges that should be allowed to connect. So just remove that default entry, which is effectively any IP address, and we'll put in the IP address of the domain controller that we're trying to allow for SMTP relay. You can add as many IP addresses or IP ranges as you need to here. Once you've got them all on the list, just go ahead and click finish. Now, the job is not entirely finished. We do need to run a couple of PowerShell commands in order to finish things off. The first command is to use the set receive connector commandlet to enable the anonymous user's permission group on the connector. And after enabling that group, we then just need to add an AD permission for anonymous login to be able to send email to any recipient. So the permission that we're granting here on this receive connector is for anonymous users to address mail to any recipient. They do not have to address the mail to internal recipients only. So we're back on the San Francisco domain controller. This is the server whose IP address was added to the remote IP range of that relay connector. So if everything is in order, this IP address or this server should now be able to connect to SMTP and attempt to relay email to an external recipient. So we can see the effect of that change. This recipient is now okay. Now, if I was to continue with this SMTP session and try to send the mail, it would go into the Exchange server's queue, but it wouldn't get any further than that because the organization does not have any send connectors yet for routing outbound email. And that's something we're going to look at shortly. But for now, what Globomantics has is the ability to relay email alerts from that particular server to any internal or to any external email addresses. So let's wrap up this module here. We had a look at the transport pipeline and some of the key terminology when it comes to transport and internal mail flow. We also looked at how internal mail is routed by Exchange within the organization, how shadow redundancy protects our email in transit, and then how SafetyNet builds on that by storing mail that can be resubmitted to prevent any data loss. Finally, we took a look at the default receive connectors on an Exchange server and how to create a custom relay connector as well. Coming up in the next module, we're going to look at establishing internet mail flow.